Okay, I did the FP problem today and I corrected it. I did it a long time ago, but now I'm correcting this. So what I have here is a fold fusion question that is like really, really fold fusion, like really all in sort of thing. Like 20 marks are basically almost all on the three conditions, as well as just understanding how you can write it in terms of fold fusion. So here they're pretty generous and they gave the definition of fold, pretty standard. And then the fold fusion law is here. And then they gave the three conditions, one, two, and three. And part A asks, briefly outline the proof of the fold fusion law with sufficient detail to account for the adequacy of the three conditions. Okay, so for part A, they already gave us the three conditions. We're going to explain what cases we require each one. So this is the general formula, and then we just think about the different cases we have. In the first case, we have something known as bottom, which is just any kind of illegit argument, such as going to infinity, such as just an expression that doesn't make sense. So if we have bottom, that requires strictness of f because if we have the fold here, it would give bottom, and on the right hand side, it would give bottom. So f of bottom has to equal bottom, so that means f has to be strict. And then the second case we would have is when the input is a list. In the case that it's a list, we have the fold inside here, the fold GAXs turns into just A by the definition of fold. And then on the left-hand side, we just have f of A. And then on the right-hand side, it's just B. So f of A has to be B for the second condition. And then the third case we have is just we have a finite amount of stuff that's non-empty. For this, we just assume by our induction hypothesis states that we kind of this expression holds. So then if we're going to do this, we're just going to add one more element to this. And then we can apply the definition of composition because F composed of this would just be that thing inside the bracket. Next, what we have is that the definition of fold. So for that, we just basically expand out the g of x outside of this fold so that g of x is before the fold, and then we have x's over here. Then we can apply our assumption up here. We know that f of g of x is equal to h of x of f. Basically, f of g of xy, it's just like we're applying one more argument here so that this is holds. I think the major thing here is to kind of think of this as a branch. Basically, one is a branch where you have just f on one side and then your g of g branch. And that h is just basically moving that f branch along the thing so that we get to the other side. And then we just have all of it as h. That way we don't have to do the composition every time, we just do it once. So here, when we just kind of match the thing, when we have g of x of fold of this, um, this is basically matching the form of f. F remains the same, f and f, g and g, x and x, and then y. Y is this fold expression over here, so that's y. So then in terms of just writing it in terms of h, we would just have h of x of f of y. Y is this fold expression, so it's this thing over here. From this point, we can just apply our induction hypothesis because we know that fold of R of G of A x's is just this thing, right? So then we're going to just, f of this thing is equal to that thing. So we can just replace it in terms of this. And then we're just going to apply the fold definition again and just put h of x back into this expression. And we're back at, and f of A is B. So we have our fold of HB of x composed of cons x's is equal to this. So this holds for all of it. So that's why the third condition is true. And for part, and then the last part that's sort of implicit but still a good idea to mention is about the infinite case. When the equation is chain complete, since it consists of complete Haskell definable expressions. So the argument applies, and then that's why it's true for infinite arguments. Okay, moving on to part B. Explain briefly how fold fusion can be used to calculate an implementation of a given f of A of list to B as a fold when this is possible. Okay, so we're given such a thing and we want to write it in terms of fold. So the major kind of takeaway here is that if we want to write something as a fold, and there's no way we kind of can write this, we don't know what f is. So the only thing we can do is kind of apply something that's already a fold to f, and then use the fold fusion law, right? And the simplest thing that we can do to not change anything up is to use the identity function, which we have here. Fold R of cons of an empty list is just the identity function, recreating the list, right? So what I can take advantage of is f is just equal to f composed of this thing. And then I would be able to see that f is equal to f, g is equal to the cons, and then a is equal to the empty list. And I'm going to be checking the three conditions. F is strict, f of a equals b, which means in this case, f of empty list is equal to b. And then the third condition, f of g of xy is equal to h of x of fy. So then I can just take, I know my g is this, so I substitute it back. Then I just rewrite this in terms of this form. From here, what I can do is I can expand f of x's to get something with some kind of operation and then f of x's. So then from that, I can just substitute f of x's as accumulator. So on the left-hand side, I would have h of x of accumulator. And on the right-hand side, I have whatever this f of x of x's is in terms of the accumulator. That would be what I would do. Moving on, part C. We're kind of switching gears slightly, but still the same idea. Standard function concat of this form might be specified by this. If it were the case that concat fold R or fold or PQR for some PQR, what would be the types of them? So we're just trying to find if we write it in this form, more PQR, right? For these types of questions, how we're going to approach it is just breaking down to what is our input form, what is our output form, what are the variables we have here, what are their types, and then just breaking it down step by step to find what we need. So we first have, we know we concat takes a nested list and 2 dimension to 1 dimension. So our type is this. This means that this thing returns this, so it's a single list. Next, what we have is that our return value is a single list. So that means our base case should also be a single list of the same type as return value. So that makes our life very easy for R's. R is just a list of A. Next, what we can do is because we know fold has this form, x of type has type x goes to y to y to y to list of x to y, then what we can do is kind of just match what we have, right? We're given that y is a list of A because that's the output. Then we have our x. Here we know that we're inputting a 2 dimension list, and then the thing that we're inside here that we're supposed to input is a list of x. So that means that in reality, what x represents is just a list of A. So then, yeah, basically the outer fold takes this and then returns that. So inside here, we now can dive into what P and Q are, right? So to find what P and Q are, we see that P and Q are inside this smaller fold function, inner fold function. And the inner fold function is of type A to A to A. That's because inside here we see that the fold of this is just this function, right? So then that has type x to y to y. So x to y to y because x and y are both list of A, so that's how we got the A to A to A. And then this is just a partially applied form because we have fold of PQ. So then in reality, if we were to have a second expression of the fold, then we would have, let me erase this. If we were to have a second form, this was the initial. Then if we were to have inside the second one, how it would be split is P is this and Q is this, right? So this is what our P and Q are. So the remainder of this type would be the rest, right? So then inside here, our list of X would just be the list of A, and then the list of Y, I mean the Y over here. I'm just matching. List of X should be equal to, let me erase this so it's more clear. Let me use a different color. So list of X over here, I'm matching, is should be this. And then the Y over here should be this. Why is it this case? Because it's right associative for type, so that we can treat it as there's an implicit bracket over here. And then we just have two elements, X and Y. So over here, we know that the list of X is equal to type A, and then that means that X is equal to A. And then for the blue part, we have that Y is equal to this thing over here. So then we can just work backwards, right? P fold of PQ. P is like the first part. If P is the first part, P is technically X, Y, Y, right? That's what P is. If P is this, it's X, Y, Y. So then I know what X and Y are. So I just substitute this in, and this would be my P. And then the same logic for my Q. My Q would just be the Y over here. I'm gonna color it yellow then. If I color it yellow, then my Y would just be this thing over here. So then it would just be A to A. So that's how I find my type of P and Q, and R was found much earlier. Okay, moving on to part D. Show that concat can be written as a call fold R. Okay, so this part is just looking at the condition and doing it again, right? Actually concretely doing it. Concat is strict as it evaluates its arguments, so we're good on that because it has to go through the whole thing, right? In the second condition, concat of empty list is equal to empty list, so our base is just equal to an empty list. And then our third condition, f of g of xy is equal to h of x of fy. So inside here, our f is concat, our g is the cons, our x is technically an excess. We're going to write it as excess because concat takes a list as argument rather than a single element. And the same idea, y would just be before it would have been the list. Now it's a list of lists. So this is just how we write the same form of what we just had in terms of these variables. Next, what we do is we just clean it up a bit, concat of x's, cons, excesses. And then on this side, it would just be the same. Then what we can do is this is just a reverse swap, just like because I want to keep the h because I want to find what h is. So I'm going to move the h to the left-hand side just because it looks nicer. And I know that concat, like the idea behind the definition of concat, is that I have x's, which is my first list, and that I call concat on the remainder of that list, which is like the recursive part, and that I would like add those together. So that's my plus plus together. So then that would just mean that this thing, because I have the x concat x's over here, concat x's and concat x's. So I just call this accumulator. So then h of x's accumulator is equal to x's plus accumulator. So I can definitely see that by this point h is plus plus. So I can write concat as simply fold of plus plus empty because here I said fold is equal to hb. And h is this, b is that. So that's part D. Part E, we're trying to use fold fusion to show that the argument in fold R in part D can itself be written as a call fold R as in part C. Okay, so what this means essentially is that we have to kind of get it into that format. How we're going to get it into that format is definitely we see that it was fold into fold. Like it was, can't remember where it was, but part C. Yeah, it was this form, fold, fold into that. So then that means that whatever our plus plus is, we have to kind of expand that and write that as a fold before we can write the whole thing as that form. Yeah, we need to find plus plus, which is the inner fold. So we're going to check the conditions again. C1 is true because plus plus is strict in the first argument. It definitely has to see what it is, but it's not in the second though. That's something to keep in mind. C2, the condition is that plus plus of an empty list of y's would just be y's, right? So our Q is essentially just a identity function and it would be our base case. In our third case, we have um, the classic f of um, h, like basically the idea that we have f of that thing over here is h of x of f of y. So then inside here specifically, our h is the p, and then our f of x is the y that we usually have, and the f of this thing. And then what we can do is um, we know that f is plus plus. And then to apply these arguments, we just apply y's on both sides so we can kind of simplify it. So on the right-hand side, we can kind of work around it. We can just put x in the front and then first do x's plus y's. Then what we can do is we can see that it's this form. Then what we can do further is we just call plus x's as a k. So then on this side we have also plus x's. So that's why on this side we have pxky's is equal to x cons ky's. So then over here we see there's y's on both sides, and then this is actually composed because we're kind of treating the function like the accumulator as a function rather than a a list, because we have a second list. We have two lists over here. So we have to have the second list in order to put the first one in, right? So we're going to return a function. P of x of k is equal to x cons composed with k. So we can write concat fold of p id empty, where p of xk is equal to x cons composed with k. So that would be our answer. And then we're going to go into F. Slightly switch gears with zip width now. And then we see the definition of zip width here, which is pretty classic. There's not much to comment on that. So now we're asked to find zip width F can be written as a function called fold R. So, okay, if we're trying to write that, we're probably just going to have to also find a accumulator that is also a function, right? Because, yeah, we have two lists. So we're going to write it ideally in this form. Zip with f is equal to fold of some function with b. We're going to call it zf. Condition one, first list evaluated, so strict. Okay, yeah, that's true. Condition two, zip with f of empty y's is equal to empty. So regardless of what happens, we're going to have empty, right? So then our b would just be the constant of the empty, because we're still going to have to keep the accumulator as a function, right? We can't just write empty list, or else we're going to have a type error. And then the third part of the condition is the classic we know, f of g of xy is equal to h of x of fy. But I'm writing it capitalized just to avoid repetition because we have f here, right? So we don't want to mix up the smaller f and f over here. So we just basically plug in what we know. F is our zip with f, g is the cons, x is equal to x, y is equal to x's, h is equal to zf. So we just plug it in and we get this. From here, what we can do is we sort of I just swap the order again because I'm more interested in finding what ZF is, right? In terms of everything else. So that's why I swapped the right-hand side with the left-hand side. Then what I did was Z of f of x of zip with f of x's, and that I applied a second argument y's list because I need to evaluate, right? And then on the right-hand side now, this part, I can do some work with it because I definitely want to expand the x and x's so that I don't have to deal with it. Um, Ideally separated. So how I can separate it is break y's down into cases. If y is empty, like no, then it's an empty list. Otherwise, I would have f of x of head y's. So that would just be my first argument, applying x and y together in terms of the function f. And then zip with f of x's and then the tail of y's, whatever's remaining, and continue this operation. So then I know that I see commonalities. Both sides, the left and the right, have this zip with f of x's. So I'm going to just call it zfxs for short. So then I can make this expression zf of zfx's y's is equal to if no y's, then empty list, else fx hit at y's, and then zfxs y tail wise. So that would just be what I have. And then where, and then that would be my definition of what the ZF axis is. And I might need a definition for ZF as well from earlier. Um, Next what I have is that's just finding what ZF is, right? I have to bring it back to my zip with F. So my zip with F is the fold of ZF constant this. Empty list. And then this is my definition. ZF is this, what I just talked about, and then ZFXS is this thing. Yeah, I say this question is relatively challenging, but if you know what direction you need to go for, I think it does make sense. And then lastly, part G, we call that flip is this thing. Basically, we just swap the arguments around x and y to y and x. Keep the function the same, of course. Can flip of zip with F be written as a call photor? The minute you see 2 marks at the end of the question, you probably know that it's going to be some simple argument that makes it's a contradiction. So in fact, no, the answer is no. And it's the reason why it fails is because the function needs to be strict. Because over here what happens is we care about the argument. So before, if it was empty and we looked at the element, then we would have it is a strict function. But however, with the flip, the thing could become the second argument. And when it becomes the second argument, and when the first is a empty list, we would run into a problem where we just automatically treat it as a empty argument, which is going to return empty. We're not going to even look at the second argument, which kind of means that we aren't strict anymore. So fold fusion cannot be used. So then that would mean that we would fail the test. Okay, that's it for this question.